Hi, my name is Daniel Jing Shern, student ID 20458621, presenting my assignment 1 for finite element analysis of a beam-link spring system subjected to a distributed load. Here is the problem overview for the assignment as well as the given data. We can see from this diagram here, the beam is hinged at point A and is supported by a link at point B. The link is from B to C. This beam has a specifications and dimensions of 150 mm, which is a universal beam, and as well as 14 kg per meter length. The length of the beam is 1.8 meters, and the link cross-sectional area is 2 times 10 to the power of -4 meters squared. The vertical and horizontal dimensions for H are equal of 1 meter each, and this beam is supported by 8 equally spaced springs as shown here in the figure. Lastly, the beam is subjected to a load following this equation in this figure. To start the modeling of the geometry, I first created a coordinate file from txt using the Notepad app in my computer and imported it into ANSYS Workbench itself. This is then followed by applying cross-sections as per assignment questions. There are 2 cross-sections that are present, the beam as well as the link. Here shown are the dimensions for the beam as well as the radius for the link itself. The diagram here on your right is the completed geometry that has been formed according to all these specifications. Based on the assignment, there are 8 equally spaced springs, and the spring stiffness values is determined from the student ID digits using this table here as shown. My student ID is 20458621, and the spring constant values that I've obtained from this table are tabulated here on your right. The springs are attached directly to the nodes of the model with the spring length of 0.25 and varying spring stiffnesses for the longitudinal stiffness. Here on your right, you can see the completed model with the springs attached. To apply the boundary conditions, I use the remote displacements for point A as well as point C. Here I've set the XYZ components to be 0 magnitude, as well as the rotations for X and Y axes. However, the rotation for Z axis is free. Moving forward is the meshing as well as the APDL command. The element sizes I've selected here is 0.01, and you can refer here to the APDL code where there are 180 intervals. Each interval is increased with the increment of 0.01 followed by the mesh size. Down here is the equation used for the distributed load. The results for the deformation along the y-axis are shown here with the maximum deflection and minimum deflection values displayed shown here. This is the same for the deformation along the x-axis with the values shown here on your left. The forces for link BC are determined using the axial force, and it is noted that the force acting on this point itself is about 77,000 Newton. The reaction forces at point A are separated into 3 orientations, and the values are listed here on the right. This is also the same for the reaction forces at point C, where there are 3 orientations and the values are listed on the right. As mentioned, there are 8 springs in this system, and each spring has a different spring stiffness. Here are the data for the forces that are being applied on the spring as well as the elongation of the spring. The interpretation and assumption for this assignment is that the interpretation is that y-axis deformation shows spring reduce the midspan deflection. The second one is that the spring forces results that are uneven is due to the fact that there are varying stiffnesses as well as different load distributions. Lastly, for the final interpretation is that a link supports the load, hence why the axial force is so high, which reduces the vertical deflection of the beam. Following this, several assumptions have been made. Number one is that the structural steel was the selected material for the beam and link. This is followed by the Young modulus and Poisson's ratio for the beam and link to be the same, whereby the Young modulus is at 200 GPa and the Poisson ratio is assumed to be 0.3. Lastly, the final assumption made was that the spring length remained constant of a value of 0.25 meters. In summary, the assignment question for this beam link spring system was successfully modeled using the ANSYS software. Challenges that I've personally faced for this assignment are these two: applying varying distributed load correctly, as well as mesh sizing to be aligned with the line elements. What I've learned from this assignment is that the boundary conditions that are initially set will strongly influence final data accuracy. This is also the same for mesh, so mesh refinement will further improve reliability of the system. Lastly, is I've gained confidence in translating physical systems into finite element analysis models. Thank you. That's all from me.